In this video, we'll talk about higher order derivatives. So the idea behind a higher order derivative is actually pretty simple. You basically just keep doing this differentiation process. So for example, we'll just take a real easy function here. Say f of x is just x squared. So in class we did several examples of this, both with the limit definition and the new power rule, to say that f prime of x is just 2x. Okay, so this function right here, f prime, we're going to call the first derivative of f. And now what we're going to do is, if we've got the first derivative of f, then you might suspect that there might be more of them. So the next one that we'll write down is the second derivative of f. Okay, now the notation for this will be, well, 1 prime is first derivative, so how about 2 primes for the second derivative, and then so on. Now, what does it mean to take the second derivative? Basically, all this is it's the first derivative, the derivative of the derivative. Okay, so if we looked at the function that we have right here, and let's pretend that that was the original function we were given. What's the derivative of 2x? Well, it's just 2. And so the second derivative of x squared is 2. One derivative gets me here, so just sort of draw arrows. And then another derivative gets me here. And we could continue this process as much as we want. So the next derivative will have 3 primes. And now we've taken the derivative of a constant, so that's 0. And so all the rest of them from here would also be 0. Now, once you get 3 primes, that's as many as you ever want to write. So you would never, for example, write for the fourth derivative, you would never write f with 1, 2, 3, 4 primes. It's just a little bit too cumbersome. So instead of writing this, what we'll write is, there's two versions, f with a 4 in parentheses. And the parentheses here are actually kind of important because we don't mean raising f to the 4th power. We just sort of mean 4 prime marks, 4 derivatives. And a way around the problem of making it look like an exponent is actually to use a Roman numeral. Like that. So, and you could do this, of course, for any higher power if you want. Now, one other piece of notation, this has all been Newton-style notation. You could also write this as d to the 4th of f over dx to the 4th. And this symbol right here is the Leibniz notation for the 4th derivative, whereas this one over here, these two, are sort of Newtonian style notations. And you'll see both of them in the book, and we'll use both of them periodically in class. Okay, so let's work a slightly more complicated example of this. So let's say instead that we have f of x equals, and I'm going to do x to the 4th plus 2, oops, let's erase that, plus 2x cubed minus 7x squared minus 4x. I'll clean that up. Okay, so now we have sort of an honest polynomial. And if this is our original function, we're asked to find the second derivative. Okay, so here's our function. Find f double prime of x. Okay, well, the first stop along the way is just to figure out the first derivative. So first we'll calculate this. And we'll do this using the rules that we learned on Monday. So the derivative of x to the fourth is 4x cubed. The derivative of 2x cubed is 6x squared. The derivative of 7x squared minus 7x squared is minus 14x. And the derivative of this is just minus 4. And then we need to add up all the answers. So we need a plus here. We'll leave the minus there and the minus there, right? So this derivative's here, this one there, that one there, that one there. And the sum or difference rule means that we can just take each piece individually and then add all the answers up. Okay, so that's what we got. All right, so that's our first derivative. And that's great, but it's not what we were after. We were after the second derivative. So just like before, the second derivative is the derivative of the derivative. So we'll just do this process again. So I've got f prime. We'll take the derivative of this line to get this line. So the derivative of 4x cubed is 12x squared. The derivative of 6x, that's a 2 right there, by the way. The derivative of 6x squared is 12x. The derivative of minus 14x is minus 14. And the derivative of 4 is 0 because it's a constant. So I'll go ahead and write plus 0 here, but we really don't need that. Okay? So all we did was just keep taking the derivative. Did it once, did it another time to get the second derivative. Not a big deal. Okay, so let's look at one more example of this. Let's say instead that we have the original function was 5x to the 3 halves. Now, as we discussed, the power rule works provided that the power is a number. It doesn't have to be a whole number, although it certainly was in the previous two examples. Here it isn't. Okay, so but the rule still works. So the first derivative will be 5 times 3 halves x to the 1 half. And then we could simplify that just a little bit as, say, 15 halves x to the 1 half, or if you want, 15 halves square root of x. But I'm going to go ahead and leave it in this form here for right now because we're not finished. The second derivative is just the derivative of the derivative. So we've already computed the first derivative. That's this guy right here, or say this form. We'll use the orange form because it's a little bit cleaned up. So what's the derivative of this? Well, the 15 halves stays put. The 1 half is going to come down. X will be there, and then we'll have x to the, well, the new exponent is negative 1 half because we take 1 away from our exponent. Okay. And now let's just simplify this a little bit. So 2 times 2 is 4, and this is a negative 1 half as an exponent, means it's a square root in the denominator. So we could write this as 15 over 4 square root of x. And that looks much nicer. Okay, so you can do this for even higher derivatives. So the third derivative, as we said up here, would be the derivative of the second derivative. And the fourth derivative would be the derivative of the third derivative, and so on. And so they form a little chain, and if you want to go as far down as you need to go, then you can do that without any difficulty. Now, one thing I thought I should mention is just sort of the names that we have associated with this. So in a physics context, we said that the function originally here was the like a position function, and then the derivative is velocity, second derivative is acceleration, and the third derivative actually has kind of a cool name. It's the jerk. So you can make all sorts of jokes about that if you want. But for the most part, there's rare instances where you need to go to the fourth derivative and higher. There's one example that you'll see in Math 112 if you go on to take that, where you do in fact need the fourth derivative of something. But for the most part, going down 2 or 3 is enough to get the idea. And yeah, so see you in class.